Hello there, welcome to a concept session. So we are going to carry on our conversation from the definition of kinematics. So in the kinematics, we're trying to describe the motion itself, the various things that we need to describe the motion. So you have a displacement, position, velocity, and acceleration. And we learned that the most fundamental thing to know is position with respect to some fixed point. So this is like a origin is a reference point. So once we put a reference point with respect to which wherever the object is at that instant, that vector in the space is going to be position vector with respect to that origin O. But we don't want to be actually tied to a reference point. Then we discover concepts like displacement, which are independent of the choice of the origin. So we have like an infinitesimal displacement, vector. So we go from R, T, some position, to an instant later it is P, and now it's a little bit later P is moved over there. So this is at time T, and this time T plus delta T, and so this position vector is called RT plus delta T, and displacement is this. And although these guys were with respect to that, this displacement, which we denote by delta R, is independent of O. Although R and R at T plus delta T depend on O. And so we had a definition of infinitesimal was delta R is infinitesimal displacement in the limit delta T goes to 0, but delta T is not 0. This is coming from concept. This concept is coming from calculus. So it leads to a couple of interesting thing. We call this kind of thing like a dr, and we get a velocity at instant t. So this is not times t, but at t is dr dt. So this is abstract, and when we write down in terms of x, y, z, then the dr becomes this vector becomes just dx, dy, and dz. So in the event of more concrete, so this concrete or in components, the velocity becomes dx over dt, dy over dt, and dz over dt. And position vector r of t, that just becomes x, y, z, and each is a function of t. And if you wanted to write down in a vector notation, it will be like I hat plus y of t, j hat plus z of t, k hat, and I hat, j hat, k hat are the unit vectors. So like along this is I hat, along this is j hat, along this is k hat. Okay, so this is abstract and this is concrete. Similarly, acceleration at some time t in an abstract way will be how the velocity changing. So we look at a velocity vector at some time t. So maybe the velocity vector at time t is like this, and velocity vector at some other time, velocity vector at time t plus delta t looks like this. So from tip to tip we'll have difference of that. So this will be delta v during these times, and so as delta t goes to 0, this will become dv, this will go to dv, and so this is just a dv dt, but this is abstract, and this whole process is abstract. But you can do concrete again, and concrete will be acceleration will be equal to x component. So this is a v, the way we write down is v sub x. We call this v sub x. That's a function of time at time t, and this is v sub y at time t, and this is v sub z at time t. So these are functions of time, and sometimes we just suppress t. So this is a dvx dt, dvy dt, dvz dt. Okay, so this is abstract and this is very concrete. So all the we want to be able to go from you can see if this is the direction that if I give you r of t, suppose I give you that, then yeah, that means I give an x of t, y of t, of z of t. From there you can do the derivatives, you can get that. So you get vx, vy, vz, and then you can take the derivatives and you get these guys, and hence you get the components of the acceleration, from which you can figure out the magnitude of direction and direction of the acceleration. Okay. Okay, so I just summarize it here. So given this, by taking successive derivative, you can get the velocity components, and from these components you can get the magnitude of the velocity vector and direction of v, as in a video earlier we did. And then we take this components again, and then you from these you can get the magnitude of acceleration and the direction of acceleration vector. So you can get this. So you're going from given position information at all times, which is a smooth function of time. We can get this. Of course, you can get that from position vector magnitude and direction of r. So this given, you can get the components, and from the components you get the derivatives, and from the of the velocity vector, and from the components of velocity vector you can construct acceleration. Okay, now we want to do now is go given this. So now we're going to do given this, get v of t and get r of t. So or you can given v, so this one problem which start from acceleration given and go all the way there. Another may start from given v, you get r of t. We'll find out that this is just an integration. Start from here to there is an integration, and I'm going to lay that out now. If you have done calculus before, this is just going to be a review. You're going to be very familiar with all the things we're going to get. Okay, so this is our task. Say, how would we go about it? Well, we're going to look at this as we need to find its component, Vx, Vy, and Vz. And each one of them going to set up the equation. So from definition, we have dvx dt is ax. So we're going to plug that in here. That's going to give me dvx dt is equal to that's going to be and then I'm going to multiply by both sides with a dt on the other side. So that just gives me dvx is going to be ax, which is a function of time. Could be constant, could be function of time, and dt. And so you can see this should be true. Then what is also true is integration on both sides. And so if I time t is say goes 0, at that time I need to know what the vx. I'm going to write down v0x for that. So these are, I choose some initial time and initial x velocity. So like initial time instant and initial x velocity or x component velocity. And we can leave this at the upper limit, will arbitrary time t, and at that time vx is going to be velocity vx, which will become a function of t because this t is arbitrary. So if I can do this integration on the left side, is very easy to do. We have a vx minus v0x, which is this going to be function of time, and this is constant because I picked an instant, and over there it's just going to remain unless I know what that is. This cannot come outside the integral, so this have to be done depending on what that is. Ax of t dt. Now, similarly, if I have a dx over dt for vx of t, that's the definition for relationship between dr dt equals to v. From there the x component is going to come out like that, and it just looks like that kind of equation. So it's again be dx will be vx function of time dt. So this will require a different kind of information. So let's see, I start from t0 because that's integration variable, sometime t. Again, this cannot come out unless I know it's constant. So I need to know at t equal to 0, what's the value of the x coordinate. Let's call that x0. And let's call this x, which is at the instant t, at which you can write down x as a function of t. It's going to be exactly like that. And so it's going to be x at t minus x0 is going to be again t0 to t vxt. And what happened, all of this for the x, I can do on the y and on the z almost identically, right? So start from a, not only I can go to the v, I can use that v and to go, I can use this v, I can plug it in here, and I can actually get this also. So let's do a simple example of a given a. Okay, so we want to do a simple problem. Suppose acceleration is constant, meaning it has a constant magnitude, a constant direction. So its direction is not changing around. So I can pick that direction and I can pick a coordinate system. So x-axis is along that direction, and then going to be, so suppose the acceleration is then in that direction. So I will, so this is a0, this acceleration whose magnitude is a0 and it's in this direction. So I will just say let's make this direction to be the x-axis and make that direction to be the y-axis and make that direction to be the z-axis. So I just pick axis so that when I do the component, this component comes out like that for acceleration. Now, in this thing, it's also given that velocity is like that, and position at 0 time is this way. So we need to figure out that guy. So we know from acceleration, first thing to get is the velocity at time t. So we are going to get dvx dt equals to a0, dvy dt is going to be 0, dvz dt will be 0. This is from the definition of acceleration. So these guys are very easy to do. So vy is not changing, it's going to be v0y, and vz is not changing, v0z. So this remains the same, and this gives me vx at t minus v0x is when I integrate a0 from 0 to t, t0 taken to 0, dt, and this is constant, so this just becomes a0 t, 0 to t, so this is a0 t. So it just gives me vx at time t is v0x plus a0 t. So this with this and this gives me the velocity vector. That's the velocity vector. These are the components of velocity vector. So velocity vector at some time t is simply has x component v0x plus a0t, v0y, v0z. So that's part of the answer, and then you need to figure out what that is. So I need to set that up for these guys, for how the velocity definition comes and how it's related to the position. Okay, so let's work this one out. So this just means v0x plus a0t, this should be dx over dt, and this will be v0y equals to dy dt, and this just gives me v0z equals to dz dt. Now this is constant, so this just z at whatever time t minus z0 is going to be v0z t when I integrate this out. When I integrate this guy out, is going to be y at t minus y0 equals to v0y t. Now when I integrate this guy, I get x at t minus x0 is 0 to t v0x plus a0t dt. And the right side, when we do further integration out, I get v0xt from this guy with that, and t minus 0, 0 to t, plus half a0t square, 0 to t, and so that answer is v0x at t plus half a0t square. So this position vector has components v0xt plus half a0t square for the x components, so that is the x, and then the y is going to be y0 x0 plus, because I got to put this on the other side, y0 plus v0yt, and then z0 plus v0zt. So that's the position vector, and this is the velocity vector. So you can see doing simple problems like this is no problem at all, and kinematics turns out to be just applications of these kinds of ideas. Lots of problems can be solved where they are kind of constant acceleration. One of the applications is gravity. So gravity problems, let me handle that next. So gravity problems will be, say you dropped a ball at some t equal to 0 and at rest, let go at rest. So we're going to look at t less than 0, not equal to, t less than 0. So let go at rest at t equal to 0. So nobody's touching it at t equal to 0. The ball is going to fall and the acceleration is pointed that way, in this direction, and magnitude is just a g, right? So if I take this as my x-axis and maybe the y-axis is that way and the z-axis would be that way, in this way we're thinking, then you can see that my acceleration is just g 0 0, and we got at t0 is 0, and at that time you have v is completely 0 0 0, and say this is started origin over there, and r at that time is 0 0 0. So in this way I'm choosing everything is very simple here. So I don't need to really look at these guys will not change, so I just need to look at a vx of t minus 0 for this guy will turn out to be g times t. So vx of t is just gt. X of t minus 0 integrating this guy gives me half gt squared. So this is really very simple. So v at any time, v at time t is going to be just g of t 0 0, and r at t any time will be just half gt squared for x component, and y component, z component don't change. So this is for a freely falling object, and I just did my integration. I just got the answer. Many times you put a coordinate, so y is facing above, so sometimes the coordinate is like x is this way and the y is that way. There's nothing special about that, right? The choice of coordinate is up to you, and whatever direction you want to put it and convenient for you for doing calculation, just go ahead and do that, okay? And there's nothing sacrosanct about this is as good as that, and so I just wanted to show you that you can choose coordinate x down like that. Let's do another problem. Okay, so here's a typical projectile motion problem. So I shoot a projectile from this in that direction. Is initial velocity v0, the initial position is over here, and the angle at which the initial velocity is pointed is angle theta. At some instant it's over here, and the acceleration is constant. So we can pick a coordinate system. Let's pick a typical regular coordinate system. So in this coordinate system, we are going to have, let's call this direction x, positive x, and this direction positive y. So as for the v at 0 time, is concerned, is going to be the x component of this guy will be v0 cosine theta, y component will be v0 sine theta, and z will be 0, because everything will happen in this plane. If there is no velocity outside the plane initially, so there will be no reason to get velocity outside the plane, and r vector at 0 time is all 0, 0, 0, right? How about the acceleration vector, which is constant, so I don't need to put a time here, and the way it's pointed is according to this coordinate system. If I take a component in that coordinate system, I get no x velocity. So it's like this x and y, and the vector is pointed this way. This is the acceleration vector. So it's got a negative component in the y and no component in the x. So it's going to be minus g and 0. Okay, so we already saw a couple of times because this is 0 and this is 0, so this all remains 0. So I don't have to worry about the z-axis at all. Okay, so we just look at how about the acceleration is 0, then this velocity doesn't change. So all I have to do is v0 cosine theta is vx of t. So this is the x part. I need to, x part doesn't change. How do I get, so let's make sure that dvx dt is 0 because of this. That means vx of t is vx at 0 plus 0, and integrate that, and that just makes it v0 cosine theta. Theta is the original angle, so theta is constant, so nothing is changing, right? So if I look at x of t minus x0, which is 0 because of that, and integrate that guy, I get a v0 t cosine theta, or you can write down v0 cosine theta t, because this is all constant. Integrate that, so this came from dx dt equals to vx of t. So I put on vx, so put this on that side and integrate it, I get that. So I got the x. So if I look at r of t, I get v0 cosine theta times t, and then for the z component I already have a 0, and v of t I got a v0 cosine theta, and this remains 0. So these are the only things I need to figure out.